Alright, this section in 7.5 deals with solving for special types of linear systems. To this point, you've been able to use the three different methods in order to solve systems of linear equations: graphing, substitution, and elimination. What we are looking at today is ways that we can see systems that may not always need substitution or elimination, because uh, you can see proof in the equation where it can sometimes have either infinitely many solutions or no solutions. So for a system to have no solutions, that is called an inconsistent system. An inconsistent system is a linear system that has no solutions, because when you graph those equations, um, the two lines are parallel. When you're solving for those systems, you get values for x and y, and those values of x or y are when the two lines intersect or cross. And if the lines are parallel, they will never cross. So if you put the equations into a y equals mx plus b form, and you realize that if the slopes are the same, then we can conclude that the systems have no solution, which means that the slopes would be the same and they'd have different y-intercepts. They'd have a different b. Okay? The next type of system would be a constant dependent system. This is where a linear system has infinitely many solutions. And the reason is, when you graph it, the equations happen to be the same line. You'd see the representation of two equations, but if you graphed it, you would just see one line, which means that you're just having two lines overlapping each other, which means that any uh, x and y value would intersect technically. So if you were to put the equation into y equals mx plus b form, you would find out that they're the same equation. And since they are the same equation, we can conclude that they'll have infinitely many solutions. So it's important to note that systems of linear equations can have either one solution, no solution, or infinitely many solutions. So keeping that in mind, I want to determine if our examples have one solution, no solution, or infinitely many solutions. And if it is one solution, I want to find those values. I can use either the substitution method or the elimination method. Whatever you feel comfortable with, I'll choose as I go along, determining if I need to use that at all. So the first example, I have 3x minus 4y, equals 12. And if you remember from those definitions, is I need to find if these lines are parallel or at least the same line. And the only way I can do that is if I put them into y equals mx plus b form. So my second equation, y equals 3/4 x minus 3, that's already in y equals mx plus b form. What I don't have it is the top equation. So first off, I'm going to subtract both sides by 3x, which then brings me to negative 4y equals negative 3x plus 12. So I need to divide by negative 4 to everything. So that gives me y equals 3/4 x minus 3. So my first equation gives me as y equals 3/4 x minus 3. That happens to be the same equation in my second system. So I can conclude that this has infinitely many solutions. Okay, let's go to example B. Example B, both equations are not in slope-intercept form. They're not in y equals mx plus b form. So for the first equation, I'm going to add 2x to both sides. So it gives me 2y equals 2x minus 16. By dividing everything by 2, gives me y equals x minus 8. So that's what it looks like for the first equation. For the second equation, I need to subtract both sides by 3x, so that gives me negative 6y equals negative 3x plus 30. And I need to divide everything by negative 6, which then leaves me with y here. 3 6, that ends up being 1/2 x minus 5. So that's what it looks like for the second equation. So first equation says y equals x minus 8. Second equation is y equals 1/2 x minus 2. They do not have the same slope and they are not the same line. So I can conclude that this is going to have one solution. Okay? So since it has one solution, let's find what those values of x and y are. So what I'm going to do is I want to erase what I had here, and I'm going to use the elimination method to help me solve for x and y. I'm going to multiply my top equation by 3. So then that leaves me with negative 6x plus 6y equals, it's negative 16 times 3. That gives me a negative 48. Now I'm just going to repeat 3x minus 6y equals 30. Okay, so you see how I have the 6y are alike, but they're the opposite. One's a plus, one's a minus, so I'm going to add those together. Negative 6x plus 3y gives me a negative 3x equals a negative 18. Dividing both sides by 3, negative 3, I'm sorry, x equals 6. Now I'm going to use this equation to help me out. So I got 3 times 6, which happens to be my x, minus 6y equals 30. 18 minus 6y equals 30. I'm going to subtract both sides by 18. And so that gives me what? Negative 6y equals 12. Dividing negative 6 to both sides. My y now equals a negative 2. So not only does it have one solution, but that solution happens to be at point 6 comma negative 2. Okay. Let's look at C. Neither of these are in slope-intercept form, so I'm gonna add 3x to both sides, which gives me 4y equals 3x plus 12. Dividing everything by 4, which gives me y equals 3/4 x plus 3. So that's the first equation. The second equation, I'm going to add 3x both sides, gives me 4y equals 3x plus 24. Divide 4 everything, so I got y equals 3/4 x plus 6. So here's the first equation, and here's the second equation. I notice that it has the same slope. It has the same slope of 3/4. It has different y-intercept. One's got 3 and one is at 6. So I can conclude that these two lines are parallel. And since they are parallel, I'm going to have no solution for these systems. Let's look at D. Last example. I have neither of them are in slope-intercept form. So let's put it in slope-intercept form. So the first equation, I'm going to subtract 6x to both sides, which leaves me with 3y equals negative 6x plus 9. I'm going to divide everything by 3 so I can get y by itself, which then leaves me with negative 2x plus 3. So that's the first equation. Let's look at the second equation. I'm going to subtract 2x plus, so that leaves me with 9y equals negative 2x plus 27. And this is divide 9 to both sides. This gives me y equals negative 2/9x plus 3. So even though they have the same y-intercept, that doesn't really matter. I'm more concerned about looking at the slope. So since they don't have the same slope, I can conclude that this will intersect. So I do know that it's going to have one solution. Oops. One solution. And let's find out what that solution is. So if I erase that, I'm going to use, again, I'm going to use the elimination method. I'm going to multiply, actually I'm going to multiply this by negative 3. So the top here is going to be negative 18x minus 9y equals a negative 27. And I'm just going to rewrite 2x plus 9y equals 27. I'm going to cancel out my y. Since they're opposites, these are going to cancel. So I got negative 16x equals 0. So my x here equals 0. So now just a matter, I'm going to use this equation. So I got 2 times 0 plus 9y equals 27. 2 times 0 is 0, so I got 9y equals 27. Divide 9 to both sides. Y equals 3. So my ordered pair here is 0, 3. So not only do I know now that I know that I had one solution, I know that that one solution falls on 0, 3. And that is identifying special types of linear systems. Being able to determine whether if two systems have no solution, and if it has no solution, that means that both systems have parallel lines. Um, it can have infinitely many solutions. That means that when you reduce it down to y equals mx plus b, we realize that it's the same solution. And if they don't have, if you realize that they're both going to be intersecting, then we can determine that it's going to have one solution. I hope this helps. Until next time.